So here I got 3 kilograms, and I got 2 kilograms, and I'm pushing with 10 newtons, and I want to know what happens. So one way is to just use your common sense and realize that if you push it this way, these two guys are going to move together, and know intuitively that if they move together, they will behave like an object of mass 5, and the acceleration will again be 2. But there's another way to do this, and I'm going to give you now the simplest example of the other way, which is to draw free body diagrams. By the way, when I say there's 10 newtons acting this way, you might say, what about gravity? What about the table? So imagine that this is in outer space where there is no gravity for now. So the motion is just along the x-axis. So the free body diagram, it says you can pick any one body that you like and apply F equal to ma to it, provided you identify all the forces acting on that body. So we'll first pick the body with mass 3. Here's the body of mass 3. What are the forces on it? This is certainly acting on it. Then you have to ask what other force is acting. So here is where you have to think. Yep. Anybody want to guess from the last row what force? Yes?
The reactive force of 2 on 3.
Right. So let's give it a name, right? So let's point it that way and call it F2 on 3. That's the end of this guy. Then let's look at the other fellow. Maybe you should complete the force acting on this one. Can you tell me what it is? Same person from the last row.
That the force is reacting on 2
And how big is that?
Same as F2, 3.
Right. So I don't want to give it too many different names, right? Because F23 and F32 are equal and opposite. I'm already showing F23 acting to the left. So let me give it some other name like F. Then you agree this would be the same F but pointing that way. And here is a mistake some people make. They add to that the 10 newtons. It's the 10 newtons acting on it because I know the 10 newton is pushing me and I'm going to feel it even if I'm here. That would be a mistake. That's an example of adding a force that you really shouldn't be adding. The only force acting on this guy is this little f. And that's in turn because this guy is being pushed by the 10 newton, but that's not your problem. Your problem is to only look at the forces of contact on you, and that is just this f. Then we do F equals ma for these two guys. For this guy, F equals ma would be 10 minus f is 3 times a. The other one, it will be F equals 2a. And notice I'm using the same acceleration for both. I know that if the second mass moved faster than the first one, then the picture is completely wrong. And if it moves slower than the first one, it means it's rammed into this one. That also cannot happen. So they're moving with the same acceleration. So there's only one unknown a. So once you got this, you realize what you got to do, right? This equation is begging you to be added to this equation, right? You got a plus f and a minus f, so you got to do what you got to do. You add the two, you get 10 equals 5a, and you get a equals 2. Once you got a equals 2, you can go back and realize here that f is equal to 4, and so you got really 4 newtons. Now we know the full story. 4 newtons acting on 2 kilograms gives you an acceleration of 2. On this guy, I have 10 from the left, and I have 10 acting this way, 4 acting that way. That is 6 newtons divided by 3 kilograms is also acceleration of 2. This is a simple example of free body diagrams. Very simple. If you can do this, you can do most of the problems you will run into. Just don't add stuff that's not there. That's all you have to be careful about. And the stuff that people tend to add sometimes is to keep drawing the 10 newton as acting on that. Okay, now here's another variation. I got 3 kilograms and I have a rope and I got 2 kilograms and I pull this guy with 10 newtons. What's going to happen? Again, your common sense tells you, look, you're pulling something whose effective mass seems to be 5. The answer is 2. But let's get that systematically by using free body diagrams. Now there are really 3 bodies here, block 1, block 2, and the rope connecting them. Now, in all these examples, this rope is assumed to be massless. Now, we know there is no thing called a massless rope, but most ropes have a mass which may be negligible compared to the 2 blocks you're pulling. So we'll take the idealized limit where the mass of the rope is 0. So here is the deal. 3 kilogram is being pulled by the rope on the right with a force that I'm going to call T, which stands for tension. The rope is being pulled backwards by this guy with T. And what is the force on the other side? What should that be? Who said T? And why is it definitely T and not something else? What would happen if it's something else?
If it was greater than the rope would snap. Well, if it was greater,
It won't snap, but something else will be a problem. Yes? Not only faster, what will be its acceleration? If the 2 forces don't cancel, you have a net force. What are you going to divide by to get the acceleration? 0, right? So massless body cannot have a net force on it because the acceleration of the rope cannot be infinite. In fact, it has to be some finite number, which is the acceleration of either of these 2 guys. So massless bodies will always have, like a massless rope, equal and opposite forces on the 2 ends. And that is called the tension on the rope. So when you say the rope is under tension, being pulled from both sides by a certain force. The tension is not 0 just because this T and that T cancel. It's true the net force is 0, but doesn't mean you can ignore it, right? Suppose you're being pulled by my favorite animals, the elephants, from both sides by equal force. You don't find any consolation in the fact that these forces add up to 0, right? You feel the pain. That pain is what this gentleman doesn't agree. One of you guys nodding your head. You feel the pain, you agree? Okay. That force is called the tension. So whenever you're asked in a problem, what's the tension on the rope? You're looking for that equal and opposite forces acting at 2 ends of the rope. So we don't know what it is. We'll give it a name. But by linking that T to that T, you can also figure out the same T must be exerted on this one by Newton's 3rd law. Because if this block is the only one that could be pulling this rope with T, therefore the rope should be pulling the block with T in the other direction, then I got 10 newtons here. Now you can do F equals ma for the 3 different objects. There's nothing to do here because the forces are 0, the mass is 0, it doesn't tell you anything. The first one tells you T equals 3a. The other one tells you 10 minus T equals 2a. Now again, we know what to do. We add these numbers and we get 10 equals 5a. Therefore, we find a equals 2. Once you find a equals 2, you find T equal to 6. So tension on the rope is 6 newtons. Now this is very important because when you buy a rope, they'll tell you how much tension it can take before it will snap. And if your plan is to accelerate a 3 kilogram mass with an acceleration of 2 meters per second, you better have a rope that can furnish that force and which can take the tension of 6 newtons.